All right, so today we're going to talk about a few laws that relate pressure, volume, and temperature. The first law was discovered by Robert Boyle. He discovered that if I double the pressure on a sample of gas at a constant temperature, I'm going to reduce the volume by a half. And that kind of makes sense if you think about if you're closing the container, if you're um, putting pressure on the outside of the container, you're going to have to reduce the volume to some degree. So, kinetic molecular theory, the idea that those gas molecules move around randomly, that can help explain this, because if we do decrease the volume of a gas, we're making more collisions occur. So it'd be like in the room example, if everybody's moving around randomly and I push the wall closer and closer in, we're going to see an increase of pressure. On the other hand, if I double the size of the room, there's not going to be as much collisions between the people in the room if they're all walking around randomly. So I actually have a simulation to show this. If we look at Boyle's law, we see here there's gas molecules running around randomly. If I increase the volume, you see that the pressure goes down. But if I push the piston inward and increase the volume, you see over here how the pressure goes up as the volume goes down. You can also look at the values here and figure out how they're changing as well. But when we graph it, if I keep increasing the pressure, you see that the volume tends to decrease as that pressure increases. That means they have an inverse relationship. There's an inverse relationship between the two variables when we plot them on a graph. Mathematically, what that means is if I multiply pressure times volume, I'm always going to get the same constant. So if I look back at the data on my simulation here, if I were to take 1 times 3, pressure times volume, I get 3. And if I take 2.14 times 1.40, I should also get that same constant V, or 3 rather. The constant is K. So looking here, I should get that constant K every time. So because under every condition, P times V equals the same value, I can multiply those together and end up with the same result. So P times V under one condition will equal P times V under a second condition. And we could say P1 V1 equals P2 V2. So let's go ahead and look at an example of that, of how that would work in an equation. So knowing that P1 times V1 equals P2 times V2, let's figure out what those things are. I'm starting off with a pressure of 0.947 and my volume is 150 milliliters at that point. So I'm just going to set that equal to my new pressure of 0.987 atmosphere times the volume, which we don't know. So I multiply on the left side 0.947 times 150. And in my calculator, I get 142.05 equals 0.987 times V2. So now divide both sides by 0.987. That's going to leave me with V2 equaling 143. 0.9. So 144 with sig figs milliliters. Seems reasonable. We started with 150. We ended with 144. So go ahead. Here's a question. You can pause the video if you would like to try, but I'm going to go ahead and move on. Given that this is the same type of example, this is another one. Go ahead and try it on your own if you'd like to see if you can get the answer. But I'm going to go on to Charles' law, which is now relating pressure to it's relating temperature to volume. The pressure is constant. So when we increase the temperature, the volume is going to have to increase. So on a warmer day, you might notice a balloon expands slightly, but if you put it in a colder temperature, it could lose some of its volume. You also notice that in the winter with your tires, you have to pump more gas in them in the winter because they might deflate a little bit because those gas molecules are closer together. They don't have as much energy. They're not exerting as much pressure on the outside. So at a higher temperature, the gas molecules move faster. They collide more force. So the volume of a flexible container would then have to increase for that pressure to stay the same. We can look at that again with our picture, our animation. We look at Charles' law, and we see as I increase the temperature, the volume has to increase. As I decrease the temperature, the volume has to decrease. So this was found by Jacques Charles in 1787. He noticed that the volume changes by 273rd of the original volume for each Celsius degree if we have an initial temperature of 0 degrees Celsius. Now, the problem with Celsius is that it's hard to imagine doubling a Celsius value when we have negative values involved. What would be helpful is if we had an absolute smallest temperature, absolute lowest temperature, and what the Kelvin scale helps us to do is refer to that as 0 so that we can graph the relationship of temperature and pressure as a linear one, which we can do. It's a linear effect with Celsius, but saying 20 Kelvin doubled is 40 Kelvin is much easier than those values would be in Celsius. So how do we get from Celsius to Kelvin? All we have to do is add 273 to the Celsius temperature, and that will give us Kelvin. We should be using Kelvin in chemistry for temperature. So Charles' law states that if I have a fixed mass, fixed pressure of gas, the volume will vary directly with the Kelvin temperature. We see that in the line at 0 Kelvin, we have 0 milliliters, but as I increase the temperature, I get a higher volume as well. Mathematically, it's going to look like this. V equals KT. We know that with graphs, we have the slope is given as the rise over the run. So in this case, my rise is the volume, and the run or the x value is temperature. So when we look at, if we can kind of consider this K as a slope, the slope is my rise over run, which is volume over temperature. So that volume over temperature is always going to be the same ratio, K, and we can show that just like we did with Boyle's law. We can look at Charles' law and see that volume 1 over temperature 1 equals volume 2 over temperature 2. And as long as we have 3 of those values, we can figure out the 4th. So looking at that one in terms of a problem, we can take this sample of neon gas and take volume 1 over temperature 1 equals volume 2 over temperature 2. So in this case, volume 1 is 752 milliliters. Temperature 1 is 25 degrees Celsius, but I'm not going to write that as Celsius. I'm going to convert it to Kelvin first. So 25 degrees Celsius plus 273 equals 298 Kelvin. So that's actually what I'm going to put in for T1. And then 50 degrees Celsius plus 273 is 323 Kelvin. So I'll put that there. And we don't know volume 2, but they're asking us what volume is the new volume. So I'm going to put volume 2 there. We can do a good old cross multiplication. So we get 323 times 752 equals 298 times V2. Let's do the math. 323 times 752 is a big number, 242,896. But we're going to divide it by a relatively big number in 298. And that gives me V2 equals 815 milliliters when I divide both sides by 298. So that's how we do one with Charles' law. We have one more law we're going to look at, and that's Gay-Lussac's law. Now we're going to relate pressure and temperature. Very similar to the last one. If we have the volume constant, then as I increase the temperature, the pressure inside is going to increase. That's why when you heat, if you're to heat a closed container hotter and hotter, it might burst, it might explode because that pressure inside is increasing as you heat the temperature up. So we'll go ahead and look at that one on our animation. So as I increase the temperature, notice the volume stays the same and that temperature goes way up. If I decrease the temperature, the pressure goes way down. Excuse me, as the temperature goes up, the pressure goes up. As the temperature goes down, the pressure goes down. I can also increase the pressure or decrease the pressure, causing the temperature to go up or down. So as you see on the graph, as I increase the temperature, pressure goes up as well. This was named after Joseph Gay-Lussac, who discovered it in 1802. So mathematically, similar, like I said, to the last one, instead of V over T, we've got P over T. So P over T equals that constant. And as we did before, P1 over T1 equals P2 over T2. So if we do this problem just the same way, we're going to have a pressure or P1 over T1 equals P2 over T2. Pressure of 3 atmosphere over 25 degrees Celsius. We said that was 298 Kelvin in the last problem. And we're trying to find the gas pressure at 52 degrees Celsius. Again, add 273 and we get 325 Kelvin. Again, cross multiply. 3 times 325 equals 298 times P2. 3 times 325 divided by 298. I get 3.27 atmospheres, which is just slightly higher than 3. It should make sense because my temperature went up to that certain degree there. So again, if you want to try one on your own to see if you get an answer, go for it. You can pause the video if you'd like to. But here's a summary of the basic gas laws. all three of them for you there. There's one more, Avogadro's law, which tells us that as I increase the number of moles of a gas, that's what N stands for, is number of moles. When I increase the amount of gas, the volume increases. So think of blowing up a balloon. The more gas I put in the balloon, the greater its volume becomes. So we have one last law that puts all three of these together. We call it the combined gas law. Boyle's law, Charles' law, and Gay-Lussac's law will all fit into one equation that looks like this. If I take PV over T, it's going to equal a constant, and you should be able to see remnants of each of the three equations in there. We have Boyle's law, PV equals constant. We have P over T, and we have V over T, which represents the three laws that we discussed earlier. So that can be rewritten just like the other ones as P1 V1 over T1 equals P2 V2 over T2. So let's do one more problem with that. We've got a helium balloon. I'm going to write them all out. P1 V1 T1 P2 V2 T2. So pressure 1 is 1.08 atmosphere. Volume 1 is 50 liters. And temperature 1 is 25 Celsius. Let's turn it into Kelvin. We said 25 plus 273 is 298 Kelvin. Pressure 2 is 0.855 atmospheres. Temperature 2, 10 plus 273 is 283 Kelvin. Volume 2 is what we don't know. So I can set that up with lots of variables, lots of numbers filled in. Again, P1 V1 T1 equals P2 V2 over T2. 1.08 times 50 equals, or over 298 equals 0.855 times V2 over 283. I can cross multiply everything, and I get 283 times 1.08 times 50 comes 15,282. And then I'm going to take 298 times 0.855. And I get 254.79 times V2 as well. So now I can divide both sides by that number. You want to isolate the variable, so you're going to divide both sides by the number you're multiplying the variable by. So I get 15,282 divided by 254.79, and I get 59.97, which with 3 sig figs will round up to 60. And my unit was in liters, so my unknown should be in liters. There we go. My volume is 60 liters. Here's another one for you to try with the whole combined gas law to see if you get the correct answer for that one. In this one, you're trying to find the volume again. And I just have one more point to make here. We were actually able to, long before moles, figure out different ratios of gases due to their volumes. So that's how we knew that water was 2 volumes of hydrogen for every 1 volume of oxygen, because when you would collect it in the lab, you'd get a 2 to 1 to 2 ratio. So that works for any proportion. If I reacted 600 liters of hydrogen with 300 liters of oxygen, I'd get 600 liters of water vapor. So this is the Gay-Lussac's law of combining volumes, and it states that at constant temperature and pressure, the volumes of gaseous reactants and products can be represented as ratios of small whole numbers. So 1 liter of hydrogen again with 1 liter of chlorine would give me 2 liters of hydrogen chloride. That should say, this is a typo, I believe. I think that should say 1 volume because it's 1 to 1 gives me 2. And we talked about Avogadro's law briefly earlier, but he explained the idea of combining volumes of gases, that instead of the idea that the formula for gas was HO, we were able to determine the formula for water was HO, we were able to determine that it was H2O. So therefore, the simplest format for water would be that H2O. So one more important detail we want to talk about is the idea of the molar volume of a gas. We know that 1 mole of a substance contains 6.02 times 10 to the 23rd of particles of that substance. So with oxygen, we know it's a diatomic molecule. So a mole of oxygen would be 6.02 times 10 to the 23rd molecules of oxygen. So what's interesting is that any gas will amount to the same volume for the same amount of moles. So if I had 22.4 liters of a gas, that would be 1 mole of that gas at standard temperature and pressure, which is 0 Kelvin and 1 atmosphere. So under those conditions, if I have a mole of gas, I instantly know that I have 22.4 liters of that gas. Whether it's oxygen, whether it's carbon dioxide, whether it's nitrogen, that works for any ideal gas. So knowing that, we should be able to convert liters to moles and moles to liters. So for this first example, we've got 5 liters of a gas. How do we figure out how many moles that is? Well, I know that the conversion factor is 22.4 liters per 1 mole. So let's take 5 divided by 22.4. So you get 5 divided by 22.4. And that is 0.223 moles, which should make sense because we know that a full mole is 22.4 liters. I don't have 22.4 liters, so I shouldn't have a full mole. Instead, I have about between 1/5 and 1/4 of a mole. We can also go the other way. If I have moles, I can use my conversion factor, 1 mole for 22.4 liters. So 0.768 times 22.4 is 17.2 liters. So that's how we can convert between liters and moles of any gas. Here's a couple if you would like to try them on your own. You can pause the video. But tomorrow we're going to talk about the ideal gas law. But before I do that, I just want to relate this to stoichiometry because we did stuff with stoichiometry last year, converting between grams and moles and particles, and you could do that across an equation. Well, the nice thing about gases is that the molar ratio is going to be the same as the volume ratio. So if I have 2 moles of carbon monoxide and 1 mole of oxygen, I have 2 moles of carbon dioxide. I also have 2 liters of carbon monoxide, for 1 liter of oxygen, giving me 2 liters of carbon dioxide. So we could figure out with propane burning in oxygen, we could figure out the volume of oxygen required to complete the combustion of 0.350 liters of propane. All we'd have to look at is, we know we need 0.350 liters, just multiply it by 5, and that's how much oxygen we would need. Excuse me. For carbon dioxide, all we would have to do is take that number and multiply it by 3, and that's how many liters of carbon dioxide we would receive. So that's the second lesson. It's, like I said, tomorrow we're going to talk about the ideal gas law, and we should be done with chapter 11. Thanks for watching. I know I put a lot of work out on your own questions in there. Please feel free to reach out to me if you would like any guidance on those.